So imagine for a second that you are, running one of the biggest tech companies in the world.
Okay, I'm picturing it.
Right. And you have just spent, $14.3 billion on artificial intelligence infrastructure.
That is a staggering amount of money.
It really is. You've brokered these massive industry-shaking deals. You've brought top-tier talent into your building to completely, overhaul your AI division from the absolute ground up.
Right.
And today is launch day. Today is the day you release your highly anticipated, hyper-expensive new frontier model to the world.
The big moment.
Exactly. It
Yeah.
is the one day you completely control the narrative, so what do?
Well, historically, you brag.
Right. But no, in this scenario, you publish a set of benchmark charts that deliberately show your brand new multi-billion-dollar model coming in second place.
Yeah, it flies in the face of every single marketing playbook we have seen in the tech industry the last, 40 years?
Yep.
Usually a launch day is this massive exercise in reality distortion. You cherry pick the metrics. You invent a new testing framework if you have to, just to make sure your product looks like the undisputed king.
But that is exactly what Meta did on August 5th.
Yep.
With the surprise launch of their new model, which is Muse Spark 1.2, and its companion terminal-based coding agent, Muse Code.
Right. Mark Zuckerberg just drops this on X.
And the crazy part is it actually worked. The developer community bought into it completely.
They really did.
But beneath that weird sort of counterintuitive marketing strategy is a completely new agentic architecture. It fundamentally rewrites how AI tools function on a local machine.
Oh, absolutely.
So today, welcome to the deep dive. We are dissecting a brilliant breakdown from the YouTube creator, your AI guy.
It's a great video.
It really is. He got his hands on the launch docs, ran the model through his own brutal test suite, and uncovered what is actually going on beneath the surface here.
Yeah, he went deep.
And just a quick heads up for anyone listening who manages software teams, there is a hidden pricing trap in this launch. It looks like a discount, but it is actually a massive data governance nightmare. We are going to get into all of that.
Yeah, that pricing trap is, honestly, perhaps the most consequential part of this entire launch.
For sure.
But to understand why Meta is setting that trap and why they are willing to publicly lose on their own benchmark charts, we really have to look at the massive strategic pivot happening inside that company.
Let's do it.
Because this isn't just an incremental update. It's not like they just added a few percentage points to a Python coding score,
Right.
They are fundamentally changing how AI is deployed.
Yeah.
And, more importantly, how they convince developers to actually trust them again.
Trust is definitely the operative word there. Because Meta, they suffered a massive credibility crisis recently.
Oh, massive.
Anyone who was paying attention to the Llama 4 launch remembers the fallout. It was just a complete disaster.
Yeah, they really overplayed their hand.
They came out making these grandiose claims about its reasoning capabilities. They essentially promised the moon.
Right.
And then the developer community got their hands on it, ran their own evaluations, and found out Meta was just drastically overclaiming.
The models were good, but they weren't doing what the marketing said they could do.
Exactly. They got caught grading their own homework with a really heavy thumb on the scale.
And, in the developer ecosystem, a credibility crisis is fatal.
Yeah.
It's honestly worse than a capability crisis.
Mm-hmm.
If your model is just a little slow, developers might still use it for, background tasks.
Sure.
But if developers don't believe your charts, they won't even bother copying and pasting the install script to try it out.
It's just not worth the time.
Exactly. The friction is too high. You essentially become irrelevant.
So they had to stop the bleeding. And that's really where this massive $14.3 billion scale AI deal comes into play.
Yep.
It wasn't just about buying compute or data. It was about bringing Alexander Wang into the building.
Right. They needed a totally new perspective.
They needed a total paradigm shift in how they communicated with the engineers who actually build with these tools.
And Wang's team clearly recognized the core issue.
Mm.
The old playbook of screaming, "We are number one,"
Yeah.
just wasn't working anymore.
Nobody believed it.
Right. So the new strategy they adopted is really fascinating. It's essentially this, don't claim the crown, claim the receipts.
I love that phrasing.
Yeah. They decided to make their methodology so transparent, so painfully detailed, that the transparency itself became the product feature.
Our source mentions they published this really dense 3-page methodology PDF alongside the launch.
Which nobody does.
Nobody does that. And instead of using generic terms like leading competitor, which is what everyone usually says, they explicitly named everyone.
They listed all of them.
They named the competitors' harnesses, they detailed the reasoning efforts of other models, and they showed exactly how they arrived at their own loss on these charts.
Let's look at a specific data point to illustrate just how radical this actually is.
Yeah, lay it out.
So Meta ran a kernel optimization study. They were testing how well models could speed up low-level GPU code.
Okay.
On Meta's own chart, published on their own corporate blog, they show Muse Spark 1.2 hitting a 68.7% speed up over the baseline.
Which is good.
It is. But right there, next to their own bar, they show Claude Opus 5 hitting 74.0%.
Wow.
Yeah. They literally paid graphic designers to create a chart where their biggest rival beats them by over 5%.
It's just so wild. I look at this like, it's like the analogy of the honest mechanic.
Okay, I like this. Go on.
You know the feeling, right?
Yeah.
You take your car in because it's making this terrifying grinding noise, and you are just sweating thinking you need a whole new transmission.
Oh, yeah, bracing for the worst.
Right, and the mechanic puts it on the lift, comes back 10 minutes later and says, look, it's just a loose heat shield. I tightened a bolt. You don't need the premium fix. That'll be $20.
Best feeling in the world.
Exactly. Instantly, your entire physiological state changes. You trust that mechanic with your life. The honesty does the marketing.
Because it establishes a baseline of objective reality.
Exactly. So a year later, when that same mechanic looks you in the eye and says, look, your brake lines are shot, you need a $2,000 repair, you don't even question it.
You just hand over your credit card.
Right. Meta is playing the honest mechanic here. By admitting they lose to Claude on kernel optimization, they are basically buying the credibility they need so that when they do claim a win on another metric, you actually believe them.
And our source explicitly points out that they trust these numbers more than almost any other launch material, specifically because Meta allows themselves to lose.
It totally works.
But, and we have to inject a pretty heavy dose of skepticism here, even with all this radical transparency, these tests are still vendor-run.
Okay.
They are still grading their own homework at the end of the day.
So even if they're giving themselves a B+, they're still the ones holding the red pen.
Precisely. The source notes that the pass at one metric, and just for you listening, that's a standard benchmark, measuring how often a model gets the code perfectly right on its very first try.
Right.
So that metric was averaged over 5 attempts. But those attempts were run inside Meta's own evaluation framework.
Ah, so there's a home field advantage.
Exactly. And this is crucial. While they tested competitors like Claude Opus 5, those competitor models were driven by their own respective agent products, or just generic open source harnesses.
I see where this is going.
Yeah, Meta's methodology explicitly concedes that their specific testing setup may not be perfectly tuned to extract the maximum performance from third-party models. So you are still looking at the world through Meta's specific lens.
That distinction right there between the underlying model and the harness or the agent driving it, that is actually the most important technical detail of this whole launch.
It really is the core of it.
Because the impressive scores Meta did achieve, they come with a massive asterisk. It fundamentally changes how we have to look at AI benchmarking going forward.
You're talking about the co-training architecture.
Exactly. We can't view Muse Spark 1.2 as just a standalone brain that Meta built and then conveniently wrapped in a nice terminal user interface called Muse code.
No, they're deeply intertwined.
The source points out they were co-trained. Meta actually trained the model, Muse Spark 1.2, on what are called rejection sample trajectories that were generated directly from the Muse code agent harness itself.
To really understand why that matters, we need to break down what rejection sampling actually is in this context.
Okay, the best way I can visualize this is like the mouse in a maze experiment.
Okay.
So imagine you want to train an AI to navigate a really complex software environment. You drop a digital mouse, which is like a rough version of the AI, into a maze.
Right.
The mouse runs around, hits dead ends, makes terrible decisions, and just fails. Like 999,000 times.
Lots of failure.
Lots. But out of 1,000,000 attempts, it accidentally finds the cheese 1,000 times. Instead of trying to teach the AI broad theories about how to walk or how to smell cheese, Meta simply saves the exact footprint maps of those 1,000 successful runs.
I see.
They discard or reject all the failures. Then they train the final Spark 1.2 model exclusively on the precise steps of those specific successful paths.
That is a really highly accurate way to frame it.
Hmm.
The model learns the exact sequence of tool calls, the specific syntax required to search a directory, and the exact way to format an output that the Muse code terminal specifically expects.
Right.
But the danger and the critical caveat to these benchmark scores is that those successful trajectories were mapped inside the Muse code environment.
Right. The mouse didn't learn how to solve mazes in general. It just memorized that specific maze.
Exactly. The source details how Meta used recipe tuning, specifically optimized for the way Muse code handles goals, the way it uses subagents, and a technique called context compaction.
Right.
If we look at the Artificial Analysis Intelligence Index, the trajectory is undeniably staggering.
What are the numbers?
Back in April, the Spark 1.0 model scored a 43. By July, Spark 1.1 jumped to a 51. Now, just weeks later, on August 5th, Spark 1.2 sits at a 54.
That's an 11-point jump in 4 months. That is insane.
It is huge.
It basically ties them with GPT 5.5 and Grok 4.5, though I know they are still chasing Claude Opus 5, which is at 61, and GPT 5.6 Sol at 59, and Kimi K3 at 57.
Right. They weren't at the very top.
But an 11-point jump in that short a time is just massive.
It is the fastest improvement curve of any U.S. lab right now, bar none. But because of that code training, because the model and the agent are effectively conjoined twins, the physics of AI scoring dictate that you simply cannot separate them.
You can't untangle them.
Right. The source explicitly warns that if you take Muse Spark 1.2 and try to run it in a third-party scaffold, so you plug the API into an open-source tool like OpenQuote or Klein or maybe a custom wrapper your own company built, you should expect a severe regression toward the mean.
Wait, if they are that tightly coupled, isn't Meta essentially using this co-training narrative as a sort of Trojan horse for ecosystem lock-in?
That is exactly the concern.
Like, you can't claim a 54 on the index if that score just evaporates the second I plug the model into my own workflow. The performance is the carrot, but the stick is that I have to abandon my company's custom tools and play exclusively in Meta's sandbox just to get it.
That is the exact tension developers are feeling right now. At the time our source reviewed this, there was literally zero independent reproduction of these benchmark scores outside of the Muse code environment.
None at all.
None. Meta has built an incredibly powerful engine, but they've welded the hood shut. To get the horsepower, you have to use their steering wheel.
Okay, so if we are basically forced to use their steering wheel, we need to talk about what driving this thing actually feels like.
Let's do it.
Because this brings us to one of the major centerpieces of the deep dive, decoding this completely unique agentic architecture. The way Muse code handles software engineering is a radical departure from what we are used to.
It really is.
Yeah.
Structurally, Muse code just abandons the graphical user interface trend entirely.
Yeah, no shiny buttons.
Exactly. There is no desktop app, no web dashboard. It is a terminal-only agent. If you are on Mac or Linux, you install it via a very simple curl bash script, and the binary that sits on your machine is just called Muse.
And nothing for Windows yet, right?
Right. No Windows build exists yet. It lives where developers live, directly in the command line.
Which is a really stark contrast to Claude Code or OpenAI's Codex, which have pushed so heavily into desktop apps and IDE integrations.
Very different approach.
But the interface isn't even the real story here. The structural architecture under the hood, specifically how it manages these subagents, is what actually changes the game.
To appreciate the shift, we really have to look at the baseline. The standard agentic architecture across the industry right now operates on what we call a spawn and die cycle.
Let's walk through that. What does spawn and die actually look like in practice for a developer who is using one of these tools?
Okay, imagine you give an AI system a really complex task, like refactoring an entire authentication module. The main system realizes it needs to check the database schema first. So it spawns a specialized subagent.
Makes sense.
That subagent wakes up, reads the schema file, passes the text back to the main system, and then it is immediately killed off. Its memory is wiped.
Right.
10 minutes later, the system needs to check a different part of that exact same schema file. It spawns a new subagent.
Oh, I see.
But this new agent starts with zero memory.
Yeah.
It has to completely rebuild its context window from scratch, reading the exact same files all over again, just to find one new piece of information.
I look at that like working with a junior assistant who has like a 10-minute memory span.
Yes, perfect analogy.
Every time you ask them to fetch a new file for a project, you have to sit them down, re-explain what the company does, re-explain the overarching goal of the project, and give them a map to the filing cabinet. Also, they can grab one single document.
Exactly.
And the moment they hand it to you, they forget everything again.
It is incredibly inefficient, both in terms of latency and compute cost. Every time you rebuild a context window, you are burning tokens and wasting time,
Just throwing money away.
pretty much. And this is where Muse Code's architecture is genuinely revolutionary. It utilizes what Meta calls persistent async background agents.
Meaning they don't die.
Exactly.
Yeah.
When Muse Code spawns a sub-agent to investigate a database schema, that agent stays alive across the entire session.
Wow.
It remains resident in the background, it maintains its localized context window, it carries out next steps autonomously, and it has the agency to decide when it actually needs to report back to the main thread.
So instead of the amnesiac assistant, you have a dedicated specialist who actually remembers what you both did all morning and can anticipate the next step without you having to rebrief them every 5 minutes.
The benefits to workflow efficiency are massive here. The source outlines how this directly improves multi-step task completion. Because the agents stay alive in the background, they aren't rereading the same dense configuration files 4 different times.
Right. The data is just there.
There is vastly less redundant context gathering. This severely reduces overall latency on long tasks.
And from a human perspective, it just dramatically lowers the cognitive load.
Oh, for sure.
Anyone who has tried to get a standard AI agent to complete a massive coding project knows the exhaustion of having to constantly jump in, fix its context, and point it back in the right direction.
It's exhausting.
But if the agents are persistent, they know where they are in the work tree. They require significantly less babysitting from the user.
They do. But persistence introduces a new, honestly terrifying problem.
Oh.
If you have a single agent running a task for 5 minutes and it crashes, you lose 5 minutes.
Annoying, but fine.
Right. But if you have a swarm of persistent agents running a massive architectural refactor for 6 hours.
Oh, no. And then your internet blips or, a memory leak crashes the terminal.
Yeah, exactly. The longer a script runs, the higher the mathematical probability of a catastrophic failure. In a standard system, a crash at hour 6 means you lose the state, you eat the massive API token costs you just burned, and you have to start from absolute scratch.
Which is exactly why developers rarely trust AI agents with multi-hour tasks. The risk of losing the work is just too high.
It's too much of a gamble.
But Meta built a failsafe for this, and it leads to what our source called the most impressive capability demo of the entire launch, the 24-hour run.
This demo is wild. Meta let Muse Code run on a fully autonomous loop for 24 straight hours, making over 10,000 tool calls without a single human intervention.
And we need to be really clear about what it was actually doing during that time, because this wasn't just like updating CSS colors on a web page.
No, not at all.
The task was writing, compiling, and profiling Triton kernels for NVIDIA Hopper KDA and MLA architectures.
Which is an incredibly dense, low-level computer science problem. To give you some context, Triton is an open-source programming language that allows researchers to write highly efficient custom operations kernels for GPUs. When you are dealing with Hopper architectures, you are managing memory allocation and matrix mathematics at the absolute lowest hardware level.
And the source pointed out they made it even harder by explicitly banning third-party libraries.
Yep.
The AI couldn't just import an existing math library to do the heavy lifting. It was forced to implement the FLA algorithm, which is flash linear attention, and that requires incredibly precise memory block management. It had to do it entirely from scratch.
That is not a task where you can just hallucinate some Python and hope it runs.
Right.
It requires sustained, logical problem-solving over thousands of sequential steps.
Right.
But the underlying intelligence of the Spark 1.2 model isn't actually what allowed it to survive that 24-hour run. The real hero of that demo is a localized feature Meta calls the event log.
The source highlighted this as the absolute sleeper feature of the launch. Nobody is putting it in their YouTube thumbnails, but it is the mechanism that actually changes the reliability equation for developers.
The mechanics of the event log are so fascinating. It is a local, append-only log sitting right there on your machine.
Let's define append-only for a second, because it's a crucial concept to grasp here.
Go for it.
It means the system is acting like a financial ledger. It can only add new records to the very end of the file. It can never go back and delete, rewrite, or erase what it did in the past.
Right.
It creates a permanent, immutable historical record of every single action.
Every single model call, every tool run, every shell command, every human approval, and every file edit is appended to this log in real time.
Wow.
It acts as an absolute source of truth for the state of the universe at any given millisecond. And because of this immutable architecture, Meta is making a very bold runtime claim. They state the system is replay exact and restart safe.
This is the part that completely blew my mind. If you are 6 hours into that Triton kernel refactor and your laptop runs out of battery and hard crashes.
The worst feeling.
Right. But the moment you plug it back in and boot up Muse code, it doesn't just look at the current state of the files and try to guess what it was doing before it died.
Right.
It reads the event log because the log has an exact step-by-step receipt of every variable, every token, and every tool state up to the literal millisecond of the crash. It perfectly reconstructs the active memory of those persistent subagents.
It resumes precisely where it stopped.
The relief that must bring to an engineer is just hard to overstate. You're no longer treating the AI like this fragile glass sculpture that you can't touch.
Exactly.
The source actually gives this great piece of advice for you listening. The very first thing you should do when you install Muse code is to deliberately test this.
Put it through its paces.
Right. Kick off a complex multi-file generation task, wait until it is deep in the weeds, and then ruthlessly force kill the terminal. Just pull the plug on the process.
It's a brilliant way to build confidence in a tool.
It takes 90 seconds to verify, but watching it perfectly resume a shattered work tree proves that the exact resume magic is real. It elevates the tool from a neat party trick to an industrial-grade worker you can actually trust to run overnight.
But having a perfect memory and being able to survive a crash doesn't mean much if the AI makes terrible decisions.
That's true.
Memory is useless if your plan is fundamentally flawed. Which brings us to how Muse code actually strategizes its attack on a code base, which relies on a set of bundled built-in skills.
The source outlines a few of the core ones. There's plan, which takes your raw prompt and converts it into a step-by-step strategy map that requires human approval before execution.
Crucial step.
Then there's timer for managing execution bounds and preventing infinite loops. There's goal, which is constantly reorienting those persistent background agents toward the overarching objective so they don't get distracted.
But the most notable skill by far, and the one that shows a really profound level of self-awareness from Meta's engineering team, is a command simply called grill.
Grill, like interrogating a suspect in a small room with a bright light.
That is exactly what it does. The entire program purpose of the grill command is to aggressively stress test and attack the plan that the model just wrote.
I love that.
It is adversarial red teaming built directly into the local runtime.
I love this because anyone who works with large language models knows the phenomenon of the hallucination of competence.
Oh, absolutely.
An AI will write a terrible plan, present it with absolute linguistic certainty, beautifully formatted in Markdown, and then confidently execute that plan right into a brick wall.
It happens all the time.
It sounds so sure of itself that you, the human, don't realize the logic is fundamentally flawed until the code throws a compilation error.
Meta knows that agentic plans fail confidently and silently. So rather than waiting for the code to fail in compilation, they force the system to argue with itself first.
How does that look in practice?
Here is how it works. Mechanically, the user issues a task. The plan skill generates a strategy. Immediately, the grill command takes that strategy and actively tries to break it. It acts as a dedicated devil's advocate.
What exactly is it looking for when it grills the plan?
It scans for missing dependencies. It looks for logical leaps where step 3 doesn't actually follow from step 2.
Right.
It searches for edge cases the plan skill ignored, or potential infinite loops in the proposed architecture. It interrogates the logic until the plan either breaks under pressure, at which point the model is forced to rewrite it, or it survives the interrogation.
It's like having a senior staff engineer ruthlessly reviewing a junior developer's pull request before it gets anywhere near the production branch.
Yes.
Except the AI is playing both roles internally in a fraction of a second. That is a massive leap forward in workflow design.
It is. But we have to look at the resource reality of this system. You have persistent subagents staying alive in RAM. You have an event log constantly writing immutable records to the disk. You have the grill command essentially doubling the workload by adversarially self-prompting every single plan.
That's a lot.
This entire architecture requires a staggering amount of compute overhead.
Right. If this architecture is maintaining persistent states and constantly running these background interrogations, the token burn must be astronomical.
It is not cheap.
How on earth is Meta subsidizing that for independent developers? Which leads us directly to the most dangerous part of this launch.
This is the big one.
On paper, Meta is offering what looks like an unbelievable, too good to be true discount. But our source makes it clear that this discount is a massive trap.
Let's break down the actual pricing structures, because the numbers themselves tell the story of what Meta is really after here. First, let's establish the baseline with the standard tier for Muse Spark 1.2.
Okay, what does the standard full price access actually look like?
The standard pricing is actually identical to the older Spark 1.1 model. You are paying $1.25 per million input tokens and $4.25 per million output tokens.
Okay.
If you use cached inputs, which you will do a lot with persistent agents, it drops to an extremely cheap 15 cents per million. And they are giving you a massive 1 million token context window with no long context premium charges.
So on its face, they shipped a vastly superior agentic architecture and a demonstrably smarter model, and they didn't raise the price a single cent.
Not a penny.
The source notes that artificial analysis calculates the cost per task on the intelligence index at roughly 40 cents.
Right.
If you compare that to the competition, GPT 5.6 Tera is 51 cents per task, and Kimi K3 is way up at 86 cents per task. So 40 cents sits right on the Pareto frontier of cost versus intelligence. It's highly competitive.
It is a very strong offering. But then right below that in the documentation is the second option, the contributor tier. This is where the trap is laid.
Same checkpoint, same neural weights, same model ID, but the price is almost entirely wiped out.
The contributor tier costs just 10 cents per million input tokens and 20 cents per million output tokens.
That is a 12.5 times discount on input and an astonishing 21.25 times discount on output.
It's basically free.
Right. For a startup trying to keep their AWS bills under control or an independent developer hacking on a weekend project, it feels like an absolute no-brainer. But nobody gives away compute at a 21 times discount out of the goodness of their hearts. How are you actually paying for this?
You are paying with your data.
Ah.
The contributor tier is essentially a massive data harvesting operation.
Yeah.
If you opt into this tier, Meta is explicitly granted irrevocable permission to use your prompts, your model completions, your proprietary code bases, your software architecture diagrams, and any internal company documents you happen to pipe into the Muse terminal to train their future AI models.
Wow. You are trading your company's intellectual property for a discount on server time.
Precisely. Now, many independent developers might hear that and shrug. They might say, fine. Take my React boilerplate code. I don't care. I just want the cheap tokens.
Sure, for a hobby project.
Right. But there is a mechanical catch hidden deep in the API rate limits that our source uncovered. This hidden throttle makes the contributor tier functionally useless for the exact persistent architecture we just spent the last half hour praising.
This is the critical insight of the episode. Let's talk about the RPM cap, because this is the mechanism that springs the trap.
The contributor tier is hard capped at 60 requests per minute, or RPM.
Okay.
To put that in perspective, the standard tier gives you a budget of 3,000 requests per minute.
Wait, really?
Yes. The contributor tier restricts you to exactly 2% of the standard bandwidth.
But wait, a single human typing prompts isn't going to hit 60 requests in a minute. Why does that limit completely break the system?
Because Muse code isn't a simple chatbot. You have to connect this rate limit back to the fan-out architecture we discussed.
Oh, right, the persistent agent.
Exactly. Remember those persistent async background agents. When you give Muse code a task, it doesn't just make one linear API request. It fans out. It spawns multiple sub-agents that run in parallel.
So if I ask it to build a new user authentication feature, it doesn't do it step by step. It might send one agent to query the database schema, a second agent to draft the API routes, and a third agent to start writing the front-end login components, all at the exact same millisecond.
Yes, and those agents are constantly talking back to the main thread. They are validating their steps, they are appending every micro-action to the event log, and they're utilizing the grill command to argue with each other over the plan.
Right, the interrogation.
All of that internal communication requires API calls. In a complex planning phase, that request pattern spikes violently. You can easily hit 100 or 200 API requests in a matter of seconds.
And if you are on the contributor tier,
The moment you hit request number 61 in a given minute, the Meta ATI violently rejects the call.
it just cuts you off.
You get a 429 too many request error. The sub-agents hit a hard wall, the parallel streams time out, the event log fractures, and the entire workflow falls over.
That is brutal. The source outlines a devastatingly common scenario that is going to play out in engineering departments across the country.
Oh, I've seen it happen.
A lead developer builds a small pilot program to test Muse code on a single, simple linear task. Because it's simple, the fan-out is small. At 60 RPM, it runs beautifully.
Yep.
The developer looks at the token bill, sees it costs pennies, and thinks, great, the contributor tier is a miracle. They deployed it to their wider team, or they asked the AI to tackle a massive multi-agent work tree.
And then
And the instant the system fans out to 6 parallel sub-agents, it instantly crashes and burns.
this is why the framing of this tier is so deceptive. The contributor tier is not a procurement decision.
Right.
It is not a financial choice a manager makes to save the company money. Because of that sweeping training data grant, and because of the hard RPM cap that structurally limits how you can use the tool, it is strictly a data governance decision.
It fundamentally changes who inside a company is even authorized to make the choice. A lead developer or a product manager cannot make this decision on their own.
No, they can't.
If your corporate legal team, your compliance officers, and your security team have not explicitly signed off on handing over your proprietary internal source code for third-party AI training, this tier functionally does not exist for you.
It is a honeypot. It is designed to capture massive amounts of simple training data from hobbyists, disguised as a budget enterprise option, but it is structurally throttled at the network level to prevent heavy industrial agentic use.
The takeaway from anyone listening is crystal clear: do not touch the contributor tier at 2 a.m. just because your token bill looks scary.
Just don't do it.
Treat it like a binding legal contract that signs away your IP, not a promotional discount code. If you want to use this model for real parallel agent workloads without giving away your company's secrets, the real price of this tool is the standard tier. $1.25 in, $4.25 out, period.
It is a brilliant, albeit somewhat ruthless, strategy by Meta to segment their user base and farm high-quality coding data for free.
Okay, so we've covered the brilliant transparent marketing, the game-changing persistent memory, the exact resume logs, and massive data governance traps.
Lots of ground covered.
But no launch is perfect, and the source video makes a distinct point to highlight what Meta's slick presentation conveniently omitted. Let's talk about the regressions. What actually got worse when you upgrade from Spark 1.1 to Spark 1.2?
The most glaring, undeniable regression is raw speed, specifically a metric we call time to first token, or TTFT.
This is how long you sit there staring at a blinking cursor before the AI actually starts typing its answer.
Exactly. On the older Spark 1.1 model, TTFT was a very snappy 2.47 seconds.
That's fast.
You hit enter, you take a breath, and less than 3 seconds later, the model is generating code. On the new Spark 1.2 model, that initial wait time has ballooned to an agonizing 26.12 seconds.
26 seconds. That is an absolute eternity in software development.
It really is.
If I hit enter on a quick command line question and have to sit there for half a minute before it even responds, I'm going to lose my mind.
It is a full order of magnitude worse. Now, the context of how you use the tool matters here.
Fair point.
As the source notes, if you are kicking off a massive 24-hour autonomous run optimizing Triton kernels while you go to sleep, a 26-second delay at the very beginning of the job is completely irrelevant. The system handles it.
Sure, you don't even notice.
But for interactive, real-time developer workflows, where you are using it like a superpowered autocomplete, asking it quick questions, expecting rapid feedback, or trying to debug a live production issue while the clock is ticking, you will feel every single millisecond of that delay. It is a brutal regression that ruins the interactive flow state.
And it wasn't just the initial delay, right? Once it finally started typing 26 seconds later, the overall throughput dropped too.
Yes, the generation speed dropped from roughly 216 tokens per second down to 165 tokens per second. Now, to be fair, 165 tokens per second is still incredibly fast. It's well above the industry median, and you can barely read that fast anyway. But it is undeniably a downgrade from the blazing speed users of 1.1 we're accustomed to.
So it's slower to start and slower to type. But the source pointed out that the regressions aren't just about speed. There is a hidden cost issue related to how talkative this new model is.
We call it verbosity. Spark 1.2 burns significantly more tokens to arrive at the exact same answer as its predecessor.
Right.
If we look at the intelligence index benchmarks, Spark 1.2 used 95 million output tokens to complete the standard test suite. The industry median for that same suite is just 65 million tokens.
So it's essentially rambling. It's generating 30 million more tokens of fluff before it gets to the point.
It manifests in a few ways. It might be writing unnecessarily long explanations of his code. It might be generating more verbose intermediate planning steps for the girl command to analyze.
Yeah.
Or it simply might default to more verbose syntax.
But the outcome is the same.
But the financial result is identical. The actual cost per task rises.
Even though Meta kept the per token price exactly the same at $4.25, because the model inherently uses more tokens to do the same job, your actual operating cost rose.
Precisely.
The source calculates that the true cost per task went from 29 cents on the old model up to 40 cents on the new one. It's a stealth price hike driven entirely by a loss of efficiency.
It is a classic trade-off. You get a smarter model, but it's slower and chattier. But the regression that I found most fascinating isn't about speed or money. It's a philosophical trade-off about how an AI should behave. The source calls it the honesty trade-off.
I found this part doubly interesting because it challenges how we read those launch day benchmark charts.
Yes, it does.
On paper, in bold font, Meta's launch materials proudly claim that hallucinations instances where the model confidently makes up false information dropped impressively from 38% down to 28%.
Which sounds great.
That sounds like a massive, unmitigated victory for accuracy.
A 10% reduction in hallucinations is huge. But the context of how they achieved that reduction is where the story lies.
The catch.
They didn't necessarily make the model smarter. They just made it more hesitant. They achieved that lower hallucination rate by making the model refuse to answer more often.
So they tweaked the guardrails.
Exactly. The source tested this heavily. The attempt rate, which measures how often the model is willing to try answering a complex prompt instead of just giving up, fell dramatically, from 82% down to 67%.
That's a big drop.
And because it was attempting fewer questions, the overall accuracy actually fell slightly, from 41% down to 38%.
This makes perfect sense when you think about human behavior. The model hallucinates less simply because it abstains more?
Exactly like a student.
Right. It's exactly like a student taking a standardized multiple-choice test who realizes they are penalized for wrong answers, so they just stop guessing on the hard questions. Their percentage of incorrect answers goes down, but only because they left half the test blank.
It's bang on.
So the real question is that actually an upgrade?
It entirely depends on the context of your workflow. As the source astutely points out, for agentic coding, this behavioral shift is a massive upgrade.
Why is that better for coding?
Because in a coding environment, a confident wrong answer is catastrophic. If an AI hallucinates a library call that doesn't exist, or invents a syntax parameter that is slightly off, the code will look perfect to the human eye, but will crash during compilation.
And then you're stuck debugging.
It can cost a developer 2 hours of agonizing debugging, digging through Stack Overflow, just to figure out that the function the AI used was a complete fiction. In that high-stakes context, you absolutely want the AI to refuse to guess. You want it to stop, throw up its hands, and say, I don't know, provide more context.
But what if you aren't writing production code? What if you are using the AI for research or brainstorming marketing copy or creative ideation?
Then it's a problem.
In those scenarios, a confident wrong answer isn't a catastrophe. It's just a bad idea that you ignore and move past. In ideation, you actually want the AI to take a wild swing. You want it to generate concepts, even if they are flawed or slightly hallucinatory, because that weird, wrong output might spark a brilliant, correct idea in your own mind.
Precisely. For open-ended knowledge work, a model that constantly refuses to answer because it isn't 100% certain is incredibly frustrating to work with. For those workflows, the older, more confident, more hallucinatory 1.1 model might actually be vastly superior to the new one.
And that level of nuance, the idea that a statistically lower hallucination rate might actually make a model worse for creative users, is exactly the kind of detail that never makes it into the polished corporate launch post.
No, it requires independent testing to uncover.
All right, before we wrap this up, we have to look beyond the text terminal and touch on the visual side of this model.
Right, it's not just text.
Because Muse Spark 1.2 is a multimodal model, and its capabilities here point to where Meta is trying to take the entire developer ecosystem.
The multimodal capabilities are where this model truly separates itself from its predecessors. The headline demo from Meta involved piping a raw video directly into the terminal interface.
Let's picture this because it feels like sci-fi. A developer takes a raw MP4 video file, a fly-through tour of a house, and just drags and drops it directly into the command line.
Yes. And Muse code takes that video, parses the individual frames, analyzes the spatial layout of the house, identifies the visual style, the lighting, and the architectural aesthetics, and then automatically generates a fully coded, visually styled vacation rental booking page based entirely on the visual input of that video.
From video pixels to working front-end React code in one step.
That's incredible.
It understands that a rustic log cabin in the video means it should use earth tones and wood grain textures in the UI. That is wild. But our source did flag a very specific failure pattern that users need to know about when generating these front ends. It's not a magic wand yet.
Right. The source refers to it as the house style problem. Across nearly all of their generations, regardless of the input, the model tended to reach for the exact same visual signature. It defaulted to the same panel structures, the same layout instincts, and the same general aesthetic logic.
It reminds me of the early days of GPT-4 where you could instantly spot an AI-generated layout from across the room because it always used that exact same standard blocky template.
It's the same phenomenon. The model is reverting to the mathematical mean of its training data. So how do developers get around that? If you don't want your new app to look identical to every other Muse Code app on the internet, what is the fix?
Overspecification. The source advises that you cannot prompt this model loosely if you want unique design.
You have to be precise.
You can't just say, make it look cool. You have to explicitly name the front-end packages you want it to use. For example, if you want 3D elements, you must explicitly demand it use 3.js. You have to describe the motion and physics of the animations explicitly. You must define the layout constraints down to the exact pixel behavior in CSS grid structures. If you give it a loose reference prompt, you get the default house style. But if you prompt it precisely, it genuinely delivers.
And when pushed with those precise constraints, it really does deliver. The source built some highly complex visual projects. They built a fully functional voxel 3D game. They built a ray-traced block viewer that had real shader logic, combining multiple shapes with working lighting and exposure controls.
Which is mathematically very difficult for an AI to generate cleanly because it requires understanding 3D space and code. But the standout example for me was the SVG generation.
The SVG generation is particularly notable because it proves the model's depth. It wasn't just generating a static image of a butterfly.
It is dynamic.
Right. It generated selectable wing forms, allowing the user to click a button and switch the code dynamically between an angular wing design and a swallowtail design. It included adjustable flutter speed parameters, real depth in the code structure, and excellent color palette work. The model does not get lazy on complex code generation when it is properly directed by a skilled prompt.
One quick warning for anyone listening who wants to build multimodal pipelines, though be very careful if your workflow relies on audio.
Yes, good point.
The source noted a glaring discrepancy in Meta's documentation. One table clearly lists supported inputs as video, image, and PDF only. But the prose text in the paragraphs on the exact same page casually mentions audio parsing support. Until Meta clarifies that contradiction, don't promise an audio transcription feature to your clients without testing it yourself first.
Which brings us to the big picture. We've talked about the architecture, the pricing, and the capabilities. But where is Meta actually going with all of this?
Let's zoom out.
The strategic shifts happening behind the scenes are monumental. First and foremost, and this is a bitter pill for many developers, open weights are dead, at least for this model and possibly for Meta's frontier future.
This is a seismic shift in philosophy. Meta spent the last few years building immense goodwill and dominating the developer conversation by championing the open source AI movement.
They really did.
Llama 2, Llama 3, they gave away billion-dollar models for free. But Muse Spark 1.2. There is no Hugging Face repository. You cannot download the raw weights. You cannot self-host this model on your own secure company server. You cannot fine-tune the base model with your own data.
They're running this completely closed. Alexander Wang's influence is clear here. He has signaled that Meta is moving toward a hybrid future. They may continue to open source their smaller, older models to keep the community engaged, but the top-tier, frontier models, the ones driving this incredibly valuable new agentic architecture, will stay strictly proprietary and locked closed behind their API.
Why the sudden reversal, though? Why abandon the strategy that made them the darling of the developer world?
Unrelenting monetization pressure. You don't spend $14.3 billion on compute infrastructure, broker massive talent deals, and completely rebuild your organizational structure without expecting a massive direct return on investment.
Wall Street wants results.
Wall Street analysts are openly demanding proof points on commercial adoption from Zuckerberg. They want to see that AI can generate direct software revenue, not just marginally improve ad targeting algorithms on Facebook and Instagram.
And Muse code locked behind a paid API is that proof point.
Exactly. It is a massive land grab for developer mindshare against competitors like Claude, OpenAI, and GitHub Copilot. They need developers hooked on their specific ecosystem. They need you relying on their persistent agents and their event log formats.
And right now, the Meta Model API is the only door to access this technology. Our source warns listeners to watch out for beta terms that can change instantly underneath you.
They absolutely will.
If you build your entire company's workflow around Muse code, you are entirely dependent on their servers, their rate limits, and their pricing decisions.
Which forces us to ask some very hard systemic questions about the future of how we build software.
It really does. So let's recap the journey we've been on today. We started with the sheer marketing genius of deliberately claiming second place on the benchmark charts to rebuild trust with a highly skeptical developer community.
A bold move that paid off.
Then we unpacked the game-changing nature of persistent async background agents that don't suffer from constant amnesia, and the life-saving exact resume capabilities of the append-only event log that makes 24-hour autonomous runs possible.
We highlighted the massive warning sign flashing over the contributor tier, emphasizing that trading your proprietary code base for a 21 times discount on tokens is a corporate data governance trap, not a clever procurement hack.
Right.
And we face the reality of the regressions, acknowledging that a 26-second delay on your first token is a steep price to pay for a model that refuses to hallucinate.
Yeah. It's an incredible piece of technology. It pushes the boundaries of what local agents can do, but it comes with heavy corporate strings attached. And that brings us to the final thought we want to leave you with today. As we look at Meta abandoning their open source roots to keep this powerful agent locked securely behind their proprietary API, consider this.
If the future of software engineering relies on locally installed terminal agents tools sitting directly on your hard drive,
Yeah.
intimately analyzing your code, writing your files that completely lose their functionality the second they lose their continuous closed-loop tether to a corporate API, does local development even exist anymore? Or is the developer's high-powered $3,000 laptop rapidly becoming nothing more than a thin client, a dumb terminal, entirely reliant on Meta's server farms to function?
Something to mull over the next time you hear a tech giant acting like the honest mechanic. Thank you for joining us on this deep dive. Keep questioning the sources, keep testing the claims in your own terminals, and we will see you next time.